Here we have two examples of a thermal break. Now, the thermal break is the process that we can use to stop that thermal bridge, stop that energy from coming out of the building and being lost and heating the street instead of heating the house, because we still have to remember that we've got to replace that energy. So here we have steel, we have a thermal break in there. There are a number of different structural products now which are out there, which we can use to actually replace or put into steel for thermal break. Very, very good. Research what is good for your particular build. Thermal break around windows. We know that we're going to have a cold bridge around windows. We can only make the most or compensate for it the best way that we can. Here we've got an insulation. We have an insulated casement, an insulation around it. There's actually very little cold bridge there. And again, it's been dealt with by design. So this will show where everything is lost, where your thermal breaks are and your thermal bridges are for your retrofit. Now, every roof connection, every duct, every corner has a thermal bridge. Everything about your existing houses is sucking energy out of the building. This is why you have to think about and take each individual connection for its own value and look at a way of compensating for that. It's not the easiest thing to do. There is some difficulties involved in doing this, but there is usually a way of compensating for any cold bridge. Retrofit. When we're doing retrofit, the cold bridging, as we've said, is so important to try and think about. There are a number of ways of doing this. This is examples of an internal retrofit, because as before, an external retrofit, most of the cold bridging will be taken care of by the actual process of putting it on and designing and actually building the outside mass around it, that thermal envelope that you're putting around it. Internally, not so easy. And we have to look at what we need to do to insulate solid walls, stone walls, bad connections, or just simple stone or brick connections to the outside. A couple of examples of inside insulation here. That is going to compensate for the thickness of the walls and bring it up to a better standard. So there's a number of insulations you can use for this. Floors. When it comes to floors, there are a number of different types. You can have solid concrete mass. There's not much you can do with a solid concrete mass other than either dig it up and replace it, which is expensive, time consuming, and is not good for your carbon count. So what we would do is we would put an insulator on the floor and potentially raise your door heads if you've got ceiling height, if that's possible. Failing that, you can only do the best you can with the products that are available, and you may just need to put an insulation over the top of the concrete with another floor to try and compensate for that heat loss, because the heat loss for your floor could be up to 30% of your property. That's how crucial this floor is. Suspended floor. A suspended floor is actually a little bit easy to deal with, but probably a bit more work, because what you've got is you've got to think of air tightness as well. Everything we do has got to think about air tightness, which is why we have good windows. Thermal bridge. Every joist is potentially a thermal bridge. So you've got 20 joists in your lounge. There's 20 points, which is potentially going to be a bridge and suck energy out of your house. It can be compensated for. Here is just one method. This is if you can take the floor up to the individual joists, suspend an airtight membrane with an insulation in between, then an insulation over the top and the floor, you've got really good thermal floor. But many times this isn't possible. You have a pre-finished floor, so you're not going to rip it up. You have to do it, if at all possible, from underneath, which means sprays and get the air tightness done, and try and compensate for any thermal bridge by putting insulation in wherever you can find to get it. There are limitations, but you can still do the best you can. If you go to the PHPP for your retrofit, it will tell you what you need to accomplish on these particular points, and that will help you come up with a way of compensating for these areas of loss. Roof connections. Roof connections is a big energy loss. You've got a permanently connection point there, which is always exposed direct to weather and cold. So this has to be compensated for. With a new build, it's quite easy because you can put it in by design, because you'll have a continuous insulation, which is potentially going to compensate for any connection point that you have in the roof. When it comes to your retrofit, you've got to think differently. So retrofit, we have an external insulation here gone up to the soffit, but in the roof, the insulation has gone right to the outside and gone down and connected as best as possible to the outside insulation. And with an airflow or cavity eaves carrier putting over the top to get airflow over the top and outside the insulation. So you've got a continuous insulation. When it comes to an internal insulation, when it comes to retrofit, all you could do is run it on the inside of the wall up to your ceiling point, and that 12mm plasterboard or whatever will be your cold spot, which you're compensating for. But you would run the insulation past the point as far as you can. That way you're minimizing any potential cold bridge. Connection points are what you've got to look at. Retrofit. When it comes to retrofit, there is a potential issue which needs to be thought about, and that is moisture. If you've got an existing outside wall and you're putting an insulation onto it, you've got a dew point, you've got a point where moisture is going to build up, because you go into airtight, you've got a cold bridge, you've got a thermal insulation, that is going to create this issue here. And this is largely because you've got two different temperatures, and that's because it's not been airtight and dealt with correctly. So, thermal bridge is exactly what it says. It is a bridge for energy or heat to be drawn out of your building or drawn out of any given area by the fact that it will conduct heat. Because if it's 20 degrees there, 0 there, the middle wants to be 10, and it will pull that energy out to try and keep it to that point. But the outside is losing heat, so therefore it wants to replace it from the heat you've got inside. And then you've got to replace the energy or the heat that's lost by your heating inside your build. This is how it works. This draws the energy out. Thermal bridge.